Mathematician, Professor of Statistics at the University of Florence, and I was just or very recently appointed Director of the newborn Florence Center for Data Science, which is a joint effort of 4 departments of the University of Florence. Indeed, data science is a kind of a new field lying at the intersection of statistical, mathematical, and computer sciences. And this is why the center is a joint effort of these 4 departments and represents, in my view, a rare, if not unique, balancing of statistical, mathematical, computer science, computer engineering, and domain-specific expertise. In fact, the 4 departments are the Department of Statistics and Computer Science, the Department of Mathematics and Computer Science, the Department of Information Engineering, and the Department of Economics. The idea of having such a interdepartmental research center at the University of Florence originated from the award that my department received as Department of Excellence of Italian Universities. And essentially in our strategic development plan, we wanted to become a reference point for data science for the University of Florence. But we realized that because data science lies at the intersection of so many disciplines, we had to go beyond departmental borders and bring together expertise around data science across the university. And our mission is essentially to create opportunities for scientists across the university to interact in new ways and also facilitate cross-fertilization in both teaching and research of expertise in data science that are already there. So today I have the sort of the difficult task of summarizing research projects and expertise of a group that is already very large. We have 12 people in the steering committee and over 100 members from the 4 departments, and we are after the kind of kickoff meeting that happened just a week ago. We already have even more affiliates from different departments around the University of Florence, so from physics as well as biology, the medical school, psychology, the lab of digital humanities, and so on. But today, well, again, our mission is not only to bring together these different expertise and creating synergies for conducting research in this area, but also to, let's say, achieve these goals by encouraging and organize network events, workshops, seminars, summer school, and short courses, and also some postdoctoral fellowship program, as well as a consulting service, not only for the university people around the University of Florence, but also for public and private entities outside of the university. In fact, we have just started a corporate membership program. So as I told you before, I have the difficult task of summarizing what our expertise are around data science. I believe that data science and artificial intelligence, the distinction between the two is rather fuzzy, just because they share a lot of important tools. However, even if they share tools, they oftentimes do not share objectives in terms of analysis. And in fact, I think that tools such as statistical learning or interpretable machine learning are fundamental, which are at the core of data science data science are fundamental for health care issues and problems when it comes especially to suggesting or recommending therapies such as in precision or personalized medicine, as well as for addressing issues of replicability and validation of results of the analysis. So even if these presentation is slightly biased, given that I am a statistician specializing in causal inference from experimental and observational studies. I think that this view that I'm presenting now is also shared with engineers and mathematicians as members of this center. In that oftentimes, especially when it comes to analyzing health-related data and health outcomes, we need not just to predict health outcomes, but we need to be able to interpret and understand why, for example, we are predicting a certain survival, or we are doing a certain diagnosis for a patient. And so the use of machine learning for making decisions is useful, but is oftentimes not enough, just because for making good decisions, we not only need accurate predictions, but we need a little bit more. We need to understand maybe not every bits and pieces of the model that generated the data, but also but we need to essentially know or understand or discover the determinants and possibly the causes that drove those predictions. And this has a lot to do with things that have been discussed this morning. So they are related to ethical. This is also important for ethical reasons. Sometimes predictions alone are discriminatory in a way. I don't have the time to go into details into this discussion, but anyway, this is a point I wanted to make. And so generally, even when we're using machine learning type methods, we want also to not just to produce predictive models, but also generative or explanatory or even causal model, because the predicting is a different task than explaining or discovering effects of causes. What I mean here is that when we need to assess the consequences of our actions, an action being also suggesting a therapy or identifying the best or optimal treatment for a patient, we cannot rely on predictors only. So, for example, this is, of course, an extreme example, but it is well known that the behavior of pigs helps predict earthquakes. But nobody would intervene on pigs to prevent earthquakes. And this is sometimes what happens is if these machine learning or deep learning tools are used for assessing or anticipating the effect of certain decisions. And so this is why we think, and this is like some examples of the type of methodological research that we are doing, especially at the Department of Statistics. The methodological research is not exclusively, but essentially around statistical learning and causal inference. And this is the methodological research that is mainly then applied in health-related problems. For example, we have developed tools to analyze broken randomized experiments, so experiments suffering from non-compliance or censoring due to death. And in fact, the EMA has recently included in the guidelines for protocols of clinical trial some causal estimate, so not just simply the contrast of means to assess the efficacy of a treatment or drug, but also the so-called principal stratum effect, which comes from our research in the analysis of broken randomized experiment. And the same or similar kind of tools are also used and developed to analyze both experimental and observational data to assess treatment effect heterogeneity, which is a topic which is sort of connected to decisions in personalized and precision medicine. And so these machine learning and deep learning approaches to data analysis can also be used to and combined with models for causal inference, but they need to be somehow adjusted. And this is what we are trying to do also with the colleagues at the Department of both Mathematics, but also Information Engineering. And they also have a lot of projects where they use neural nets as well as other machine learning type methods for diagnosis of several diseases. Here is another, now I'm going to give you just some examples of the type of applications and projects we have been involved in. But again, the type of methods that we usually develop, hopefully in the future also jointly and in collaboration with other researchers around the University of Florence, have the potential to be applied to many other instances and problems. This is, for example, just an example of the use of unsupervised learning methods to essentially define what an outlier is, instead of using the usual univariate normal distribution or multivariate normal distribution. Here, again, some non-parametric unsupervised learning methods are used to essentially assess whether multivariate values for describing the aorta are normal or not, and so requires some further attention. There are also colleagues and also myself essentially doing research in Bayesian analysis in general, and in this case Bayesian analysis is used to essentially use for profiling, in this case farms, but the same methodology could be used to profile healthcare providers or patients or medical doctors. And essentially the Bayesian machinery helps defining decision rules that are not only based on p-values or false discovery rates, but also false non-discovery rates. And so trading off both things also at the individual level. Another, let's say, area of research is in meta-analysis, and specifically in network network meta-analysis, also using Bayesian inference to do that. Another important area of research also related to health outcomes is the assessing the causal effects, and so estimating dose response function for of the air pollution or also climate exposures on health. And those type of studies are important also for assessing, for example, regulatory interventions aimed at reducing air pollution levels, or inform where to set, let's say, the bar for air pollution. And this is, for example, so we have actually, Michela Baccini sits here in the audience. She's kind of the expert on environmental epidemiology or environmental studies, and we have applied these tools to both European or Italian data, as well as conducted or we have collaborated with a group of researchers based in the US in a huge data science exercise where different data sources from satellite monitoring stations, as well as hospital admissions for the whole US, were kind of used to assess both the effect of and the short-term impact of air pollution on mortality and other health outcomes, but also to assess specific air quality improvement interventions, such as installing scrubbers on power plants, for example. This is assessing the effect of such interventions on health is rather is difficult, just because air moves. And so intervening on a power plant is not only affecting health of the people living around the power plant, but also improving health for people living longer distances. And so there is really a data science effort here, because expertise in both methods, as well as meteorological sciences and chemistry and medicine, have to be joined together to assess these effects. Another area of research, more sort of focused on also precision medicine, is using Bayesian graphical models, and in this case, for example, multiple graph for, again, finding the best treatment, or for diagnosing specific diseases. This is another example of personalized medicine using also genomic data. And again, this is another example. I don't have time to go into details here, but essentially using genomic data from different sources to, in this case, predict clinical outcomes, such as survivals, but also other multivariate outcomes. I will skip this. Again, I'm not sure how much time I have. Probably little. Okay. So all the examples that I showed you are, as I said at the beginning, applications of methods that we have been developing over the last, I don't know, 30 years, which include methods for Bayesian inference, methods for causal inference that again can be used for analyzing complex experimental studies, as well as observational studies with big data. This is why we are also adapting machine learning tools for causal inference, but also health-related research fields also include models for non-IID data, as well as non-parametric methods for statistical learning and other machine learning methods such as predictive and prescriptive analytics and also interpretable machine learning. So this is, again, because we are, let's say, so many people, it's difficult to summarize also the expertise, but I think the core of what we do and also the tools that we have applied to health-related problems, of course, these tools have also been applied, for example, to assess other things in different areas, such as, for example, we have a long tradition of collaborating with social scientists, for example. But again, those are the methods that we are typically applying to medical or health-related problems. So I think that concludes.
Thank you very much.